Salam and welcome everyone. So today we're going to be working on the question on the screen that says estimate the internal pressure of sulfur dioxide at 1.00 bar at and 298 kelvins, treating it as a van der Waals gas when internal pressure, so pi sub T equals A divided by Vm square. You may simplify the problem by assuming the molar volume can be predicted from the perfect gas equation. So this question requires us to find the value of the internal pressure of sulfur dioxide, so SO2, at 1 bar and 298 Kelvin. So the initial pressure and temperature is given. We're also told to treat it as a van der Waals gas when we use this equation. But in order for the problem to be simplified, we have to use the molar volume that we can predict from the perfect gas equation. So the first thing you have to do is remember that molar volume is basically a value you can get from the perfect gas equation. And to get that, you have PV equals nRT. Note that Vm is the same thing as volume divided by number of moles. So we have to write this perfect gas equation in terms of V divided by N. So to do that, what we end up getting is for you to just simply divide number of moles here, divide number of moles here. So what you end up is PVM is equal to RT. You can rewrite Vm is now going to be RT divided by P. So this is basically the formula that we're going to first of all use to determine the molar volume. We have to remember that looking back at the question, we've been told the pressure is 1.00 bar. Okay. We have been told the temperature is 298 kelvins. And also we've been told the internal pressure value to use, but that's just by the way. Now, of course, since this is a perfect gas equation, the gas constant R is constant, and we can use any of the two gas constant values depending on the units. So we're given pressure 1 bar and temperature 298 kelvins. I am going to be converting this 1 bar that we're given, to the proper units of atmosphere, because that is what I'm comfortable with the most. You can use bar, but just make sure that it matches the gas constant value that you'll be using to solve it. So 1.0 bar to atmosphere, we have to remember that 1 atmosphere is going to equal 1.01325 bar. So hence 1.00 bar would give you how many atmosphere. So let's just use the unknown value x. We're going to use the proportionality method to find the value of 1.00 bar in atmospheres. So this is just going to be x is going to equal 1 atmosphere bar. Okay, just hold on with me, divided by 1.01325 bar. Of course, when you have similar units, you can cancel out numerator denominator, so that 1 atmosphere divided by 1.01325. So that that pressure in terms of bar is going to be 0.97402 atmospheres. So this is the pressure in terms of atmospheres. So we have that pressure in terms of atmosphere. We have our temperature. We know the gas constant that we're using. We can just simply substitute. So Vm is equal to RT divided by P. So that would be 0.08206 dm cube atmosphere divided by mole Kelvin. Okay, times the temperature. Looking back at our question, temperature is 298 kelvins. So that would be 298 kelvins divided by the pressure, which is just 0.97402 atmospheres. So of course you cancel out sorry, this is not dm's, dm cubed. So of course we're going to cancel atmosphere, we cancel our atmosphere, we cancel our Kelvin, we cancel our Kelvin. So we end up with the molar volume is going to equal 0.08206 dm cubed per mole times 298 divided by 0.97402. We input all of this information in our calculator to get 25.106 dm cube per mole. Now, the next thing you have to do, of course, is for you to use the formula internal pressure. So pi sub T equals A divided by Vm squared. So that's how we're going to estimate the what's it called, the internal pressure. So pi sub T is equal to A divided by Vm squared. We have our Vm, we don't have our A, we have pi sub T. But remember what A is, right? A is just the strength of attractive forces for the van der Waals gas, right? in the particular container. So you have to note that the value for A is a constant and it's going to vary from gas molecule to gas molecule. So looking at the resource section of our book, we can find out what A is. So the research section of our book, which is just basically the book, this is a physical chemistry book. You can also Google it online. You can find the value there as well. So we have the A value to be 6.775 ATM, okay, DM6 divided by moles squared. So the strength of extractive forces for SO2 gas, sulfur dioxide gas, is 6.775 atmosphere DM6 divided by moles squared. So now we have the value for A as well as the molar volume. We can just simply substitute to find the pi sub t. So pi sub t is now going to be 25.106 dm. Sorry, that's a mistake. We have the A value. I was writing the molar volume up top instead of it's being at the denominator. So the value, the A value is 6.775 atmosphere dm6, okay, divided by mole squared. All of that information divided by 25.106 um, dm cubed per mole. All of this information squared. So we have pi sub t equals 6.775 atmosphere dm6 divided by mole squared divided by 25.106 dm cube divided per mole. So that's just going to be, first of all, let's square this unit. So that's going to be dm cubed squared is the same thing as dm6. Mole squared is the same thing as just mole squared. So now 25.106 squared is actually 600 and 30.3181. So now we've basically squared the denominator. So of course we're gonna do the main thing we do in chemistry. In calculations, we cancel out the units, cancel out the units. So what you end up remaining is atmosphere, which makes sense since we're finding the internal pressure anyways. So the units have to match. So that would be pi sub t is equal to 6.775 atmosphere divided by 630.3181. So that's just going to be 0.010749 atmospheres. So yeah, that's basically how it's done. Now I want to mention something because we're not actually done. Um, we have to go back to our question to see the least number of significant figures that we have in the question. You can see that 1.00 bar and 298 kelvins are the only numerical values, and they're both three sig figs. So we have to make sure we put our internal pressure final answer in three sig figs. So we're going to just approximate up until 7. So pi sub t, or the internal pressure, is actually 0.0107 atmospheres. So this is basically the answer to the question that we're given, 0.0107 atmospheres. So yeah, that's basically how it's done. If you have any questions, please put in the comment section. If you would like me to do more problems and do more questions in all STEM related courses, you could also put in a suggestion in the comment section. If you have any concerns or questions, put in the comment section. If you're a student who wants to succeed in all your STEM related courses, whether you're in middle school, high school, or college, make sure you email me at shahabitutoring@gmail.com. I am a tutor and mentor for students in high school, middle school, and college who are trying to succeed in all areas of your academic career. So if you would need mentoring as well as tutoring sessions, make sure you email me at shahabitutoring@gmail.com to see whatever services would work for you. And I wish you all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.